Good afternoon, teacher and friends. This is Team 23, and today our team will be demonstrating about our project system. I'm Ling, and I will talk briefly about the overview of this project. So the objective is to develop a system that allows a robot to navigate and able to find the exit of a maze automatically. And our team strategy is to use the brute force approach. Our system algorithms will be explained more detailedly by our team members later on. Moving on to the class diagram of our system, as you can see, there are a total of 5 main classes, one static inner class, and several relationships between the classes, such as the dependency of class robot on class main, cell, and linked list stack. But what I want to mention is that this method go in class maze is accessed by the class robot by being called in these two methods of class robot, navigate and advanced robot coordinate. And every time the method goal is called, the total steps to reach the exit gate of the robot will increase. Next, about these two classes, cell basically will be storing the current direction of the robot, and it will implement a linked list stack as the abstract data structure so that the stack will store all the directions of every cell that the robot has visited. Finally, the class main is simply creating a new robot object and call the method navigate. So now Kiet will demonstrate about our project's data structures and the algorithms.
In this project, we use the depth search algorithm to approach and solve the maze. This is the basic idea is to start from the root or any arbitrary node and mark the node and move to the adjacent unmarked node and continue this loop until all node is marked. And it will backtrack to the starting root and check for the other unmarked node and print them, traverse it and print them out. In this project, the maze is private and can only be accessed through the function go. In the function go, it has 4 directions: up, left, down, and right, and will return true if the robot move in a direction, and false when it hit an obstacle, and win when it reaches the exit. The robot function in the robot class, we use a linked list stack to store the cell of the robot that been through. And when the navigate function is called, the initiate position of the robot will be set to true and the spawning cell will be pushed into the stack. With every iteration, the robot will pick the cell on the cell on top of the stack and save it as a pattern in a temporary variable for later to be used to check for the direction. The pattern will simultaneously be added one value and can be so that the robot can advance in a subsequent clockwise direction. We we set the pattern as zero as going up, 1 is going right, 2 is going down, and 3 is going left. Uh, the code will enter a loop that will the code will continue until the result of the maze is win, and it the code will get the current cell and check current cell in a pattern and check the direction accordingly to the pattern. After, if the pattern exceeds the value of 3, we can assure that the robot has reached dead end or surrounded by a cell that it has already visited. When it reaches dead end, the robot will pop the cell that it is standing and put it in the backtrack cell variable. The backtrack cell variable will later be put into the advanced robot coordinate function to start the backtracking progress. For the backtrack in the backtrack progress, the robot is backtrack in the direction inverse. Will go in the inverse direction it received from the cell. When the robot is backtracking, the column or row is added or subtracted based on the current direction of the robot. And next up will be Kang with his presentation.
Hi, I'm Khang. Now I'll talk about the correct and efficiency of our system. So here is our way to test. And we expect that robot can backtracking when read at the end this one. So it backtracking here and can escape the main as possible. So firstly, it is our stack responding direction is pushed to here. So what you need to do is try to go up, cannot right we can. So we put the right direction to the stack. Up cannot right we can. We do again, process. Up cannot right we can. So now location robot randomize the in here location. So what you need to do is go to up cannot the wall, right cannot the wall, down the same, left is the visit the cell. So here in a dead end, and our rank will pop out this one, and now the stack is pulled to this cell. So what you need to do is first just remove this one because pop out red color of already visited. So you can go down the wall, left visited. Again, dead end, pop out, pop out. Down we cannot go off, and right we cannot visit it. So pop out again. And here the robot is as a spawning cell, so you try to go down, right down with empty display we can go, up we cannot, right cannot, down we can, empty display we can go. So now the robot is okay here. And what you need to do next, they're checking. Up cannot visit cell, right we can put the right direction. Up cannot, right we can put the right direction. Up cannot, right we can put the right direction. And here, robot is located here. And at this, what you need to do is try to go up, cannot ride the wall. So we will go down and we'll put down direction to the side. And at this stage, robot with the X-ray of the maze. Now the RAM is determined. And to check if the correct with our result in the code, I will try to show you what happened here of our code. So here is a log and here is a maze. Okay, so it can go right, right, then checking left, 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 down, right, down again. So here at the center we expect. Um, so just more sure, I want to debug this one and let you see that the stack contain the same element. Evaluate expression. Here using a English stack, so here we can see the result accent. That's good on internet. Okay. So firstly it's morning, right? And down, 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 right, right, right. It's the same. So just more look detail about the button. Here it is three, 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 two, 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 three. This button is the same, but just for remember, we start the button from zero. So add this one here, it have to be -1 instead, but we already update the button for one for the next iteration. So that's why it returns 3, 3, 2, 2, 2, 2, 3. And this one is initial value of the button is 0. So we can easily and surely that our system is correct and very efficiently when know what way to backtrack in and remember the cell that is already visited. So next, I will talk more about the time complexity of our program. Thank you.
Next up, we'll be analyzing the time and the space complexity, as well as finding the maximum steps of the algorithms. So first, we need to understand the recursion tree in order to find the time complexities. So at the spawn point, the robot is capable of traveling 4 directions, which are up, right, down, and left. So if the robot moves from this spawn point cells to another cells, it will have 4 more other options of directions to travel. So how do we find the total number of nodes in the recursion tree? So at the first layer, or level of the tree, we have 1. And then the second layer will have 4 cells, will be 4 and plus 16 and 64 and etc. So the total number of nodes in the recursion tree will then be and multiplied by m, which is also equal to the size of the 2D matrix. So to help understanding and finding the time complexities, we'll be looking at the geometric progressions. So, so we can, by replacing in A with the first node, which is 1, D is the common ratios. As you can see here, their common ratio will be 4, which is which is the same as the number of directions they have. And finally, the total number of nodes will be n multiplied by m. Replacing in here, we'll have 4 to the power of n multiplied by m minus 1 divided by 3. We reduce the other fraction, we'll get 4 to the power of n with m. However, in the worst case time complexities, the maze will be at 1000 by 1000. Therefore, the time complexities at worst case will be O to the power of n squared. And for a space complexity, the space complexities will be equal to the size of the 2D matrix or the size of the maze map. And in worst case, it will be O to the power of n. Okay, next up, we'll be looking at we'll be finding the maximum steps of the algorithms. As you notice, the robot will be traveling up, right, down, and finally left, which left will be the last direction for the robot to visit. So if the robot is at the corner, and the exit is to the left of the robot, but it was unreachable from any other directions of the path of the maze, which the only path that the robot can reach the exit will be to the left of the spawn point, of which the robot will be traveling and then have to track back to the original point and then move to the left. So to illustrate this, we'll be running an algorithm where the robot starts at 198. Here, I can see the robot will be traveling the whole map and give us the number of steps is 19,000, which we can have the number of nodes, the upper bound at 2.2 multiplied by n multiplied by m. However, this is only a blank map. We'd like to test it on a map that with a more complicated obstacles. So we're looking at 100 multiplied 100, but with more obstacle map. This time it's also start at 198. But the number of steps increased significantly to 24,000, which can comprehend to 2.5 multiplied by n multiplied by m, which in worst case of the map will be 2.5 multiplied by n squared. So to test out if this is the correct number for upper bound, we create a testing to compare. So for the testing of each at difference maze, we'll take the highest out of 3 different positions of spawning point to analyze and draw the testing result. As you can see, the testing result will always be lower than the upper bound. Therefore, the upper bound of O to the 2.5 n squared is a valid upper bound. Therefore, the biggest number of steps will be O 2.5 n squared. Thank you for listening.